everyone. Welcome to Lecture 4 of DSCI 572. So today, finally, we get to the exciting stuff. Today, we're going to discuss the fundamentals of neural networks. But before that, I'm going to introduce you to the package that we're going to be using, the framework that we're going to be using called PyTorch. And then we'll move on to the fundamentals of neural networks. So let's get started. We have a lot to cover, and I hope that we can cover everything. If we can't, I will leave some of the material to the next lecture. All right, so what is PyTorch? PyTorch is a Python package for scientific computing, and it's very similar to NumPy in that it provides the capability to us to work with basically matrix objects, but in the context of PyTorch and deep learning, we call these matrices tensors. So in that regard, it's pretty similar to NumPy, a package that provides that option for us. And one of the main important things that PyTorch does is that it enables us to use hardware that we typically don't use, and that's called a GPU or graphical processing units. I'll tell you why we are interested in using GPUs, but PyTorch basically enables computations on GPUs. Okay. The other thing is that PyTorch is really good in computing gradients, and at this point we know how important gradients are. So in the previous lectures we worked on linear regression models, and we knew what the gradient of a linear model was, what the gradient of the loss function was. However, it's not the case with neural networks. We have to have a way to compute the gradients effectively and efficiently. PyTorch does that for us. Now, let's see how. So before talking too much about the details, before introducing you to the main bits from a coding perspective, let me introduce you to PyTorch's tensors. So a tensor, just like I mentioned, is very similar to a NumPy array. So usually we call a 2D tensor a matrix, but if you generalize that to multiple dimensions, we call them tensors. So we have vector, which is a one-dimensional object that contains values. We have matrices which are two-dimensional, and then we have tensors, which are generalizations of those mathematical objects to higher dimensions. Yes? Pardon me? Yeah, could you zoom in a bit, please? Reduce the... I just zoom in. Oh, zoom in. Okay, sure. Yeah. Yeah, it's a bit too small. Yeah. Okay. Okay. All right. So at the top of this notebook, I've imported PyTorch as torch, and that's why instead of NP here, you see torch, because we're using this package. So in NumPy, we have np.array, and then we provide the values. In PyTorch, we say torch.tensor, and then we provide the values, and that creates a tensor for us. Okay, so if we check out the data type of these two tensors, we can see that instead of array, we see the word tensor here, and it says D type or data type is float 32. For the integer one, it says integer 64 for the data type. So immediately one thing that you notice is, so the default data type for floating point arrays in NumPy is float 64, but here the default is float 32. And I kind of discussed why that's the case in PyTorch, because we usually deal with large models, large data sets. We prefer to use float 32 because it's computationally cheaper to deal with, and that's why this is the default data type. Of course, we can change it if we want, but that's the default. Okay, just like NumPy, we have a lot of convenience functions like torch.zeros, ones, and also operations between tensors are also defined for us. So torch.zeros creates a tensor filled with zeros. Torch.ones similarly creates a tensor that's filled with ones. And again, we have those generator functions that generate, for example, here in this case, random values with a certain shape. And here's another example. Okay, so pretty similar to NumPy. This is why I'm going a a bit quickly through this. And again, we have this attribute called shape, which tells us the shape of a tensor in each dimension. And also similar attribute, again, just like NumPy, number of dimensions, x.ndim, that gives us the number of dimensions. So this is mainly to convince you that we are dealing with, at least at the interface level, we're dealing with a package that looks a lot like NumPy. Okay. So this is what I just discussed. If you check out the data type, you'll see float 32. However, we can change that. So in NumPy, as you can see, the default is float 64. In PyTorch, it's float 32. Okay, and we can change it if we want. So here, I specify the data type as float 64. Yes, that's doable, and that's what I get in the output. Okay, now operations on tensors. So here we have two tensors filled with random values, A and B. Let's define those. Have a look at those tensors. Okay, so this one is a row matrix, this one is a column matrix. If we add these together, because of broadcasting, we will get a matrix like this, a square matrix. Okay, again, pretty similar to NumPy. All right, we can also do element-wise multiplication. We have these convenient functions for computing the mean, the sum, and yeah, anything you can think of, basically. Okay, and so on and so forth. Okay, just like NumPy, we can index into our tensors to retrieve particular values. For example, here. Okay, this is our tensor, and look at these. For example, here I'm slicing, not slicing, I'm taking the first row, and then the second one, again, I'm doing a similar thing. And in this last one, I'm taking the first column. So that's what it looks like. Familiar stuff. Okay. Then one thing that we will need down the road is conversion between PyTorch tensors and NumPy n-dimensional arrays. Just like, for example, sometimes in pandas we want to convert our table into a NumPy array. Here, this conversion between NumPy and PyTorch is also possible. And okay, here we have x as a PyTorch tensor. And then if you use this method .numpy, it converts that tensor basically into a NumPy array. Okay.
Can you convert a NumPy array to a tensor easily as well?
Sure, yeah. Okay. So now let's get to the important stuff. So before moving on to the next section, is there any question about the interface of PyTorch? Yes.
Is there a way to do matrix multiplication?
Yes, absolutely. Yeah. So again, the PyTorch function-wise, it looks pretty much like NumPy. It has all of the functionalities available in NumPy, and it also comes with extra stuff that helps us build neural networks and train neural networks. So yes, the matrix multiplication is one of the main operations that we are interested in doing. Yeah. No, as far as I remember, no, you can't use the @ There are, for example, matmul method or the dot operator, things like that. The @ operator in NumPy is something a little bit new. So in PyTorch, as far as I remember, they don't use the @ they just use matmul. But the thing is, we usually don't deal with matrix multiplications ourselves in the context of neural networks unless you're doing some research kind of thing and you're interested in designing your own architecture for research purposes. Yeah. Okay. So, you've probably heard this acronym GPU, and it refers to a graphical processing unit. GPUs used to be used mainly for gaming because they are basically very fast at performing operations on large amount of data that is in the form of a matrix or an array. So, for example, when you're designing a game, then basically you have to update every pixel on the screen multiple times in a second, and you have to deal with a lot of matrix multiplications. And hardware designers came up with a way to, they designed specialized devices called GPUs to basically leave that task to this separate processing unit instead of putting that heavy workload on the CPU. So it is specialized solely for matrix multiplication. And then some years later, it turned out that there is this thing called deep learning, and in deep learning we do a lot of matrix multiplications. So it was just a fortunate coincidence, and people started using GPUs for training neural networks. So basically the takeaway here is that GPUs are very good at doing matrix operations. And typically, because they're specialized hardware, for example, it's not unusual to have thousands of cores on a GPU on a single computer, while your CPU might have, let's say, 4 cores or 8 cores of processing units. Okay, so the main thing that PyTorch does is that it can deal with data on GPUs. And you might say, okay, what's the big difference here? So computing on CPU, computing on GPU. Yes, it doesn't really matter that much to us because we're used to just run code and think that the code is magically running. But on the hardware level, there are a lot of effort that has to be, that people has to go through in order to implement this stuff successfully on a new piece of hardware. And under the hood, that's what PyTorch does. So it enables us to use this very straightforward interface, define a tensor, and then forget about it. The computations will all be done on the GPU very fast, very efficiently. So that's what PyTorch is good at. Okay. So there's a particular type of GPU called CUDA, which is a specialized hardware from the company NVIDIA, which they're very good at building fast GPUs. And PyTorch is tightly integrated with that framework. And you can use this code to see if you have a CUDA GPU available on your machine. I think if you have that, you'll know. So you can run this code. I don't have that. It says false. However, in May last year, something really great happened, and that's because these days, if you have a Mac device and it uses an Apple Silicon, then it has integrated GPUs inside of it, multiple cores usually. And since last year, PyTorch has enabled the usage of Apple Silicon's GPU. So if you happen to have that, you can check, actually, using this code to see if you have that. And if you have a Mac with an M1 or M2 CPU, you have that. So this enables you to do your trainings and your computations much faster than on CPU. But if none of these are available to you, again, that's no problem, at least for this course. You can do your computations on CPU as well. So PyTorch doesn't care if you don't have GPU. It's going to be slower, but you're still going to be able to do your computations on CPU. Yes?
So if I'm understanding it, you need to have a specific type of NVIDIA GPU to do computations with your GPU?
Yes. So
I have an NVIDIA GPU in my laptop, and it says false, right? So you're saying that all my computations will be no implementation of NVIDIA.
yeah, so sometimes if you have an NVIDIA GPU, you have to install specific drivers for this CUDA framework in order for it to work. So I'm not sure, maybe that's not installed, or maybe your particular GPU doesn't have that CUDA capability. So yeah, you have to check. Basically, with CUDA GPUs, you have to install the drivers. That's usually a problem.
Basically, if you don't have a CUDA GPU, there's no way to run the computations or the Mac GPUs. There's no way to use the GPUs at all for the computations.
That's right. You can't use the GPU. Yeah. Okay. Questions? So I've thrown a lot of stuff at you. There should be at least a few questions. All right, let's move on. So I have this code here. By the way, please do a git pull on the repo because I have made a few updates. So PyTorch uses this syntax torch.device, and here it accepts arguments such as CPU or CUDA or MPS. MPS is for Apple Silicon. So if you run this, if you have, for example, MPS, if you're using a Mac, it chooses that device by default, or it uses CPU. If you are not on a Mac, you can instead run this line at the top, and if you have a CUDA device, it will use that. If not, it will just default to using CPU. Okay, for example, in my case, I have an M1, and it uses MPS on this device. Okay, now, so when we define a tensor in PyTorch, we can use this argument called device, and then basically what it does, it creates that tensor on that particular device. If it's CPU, it will create that device it will create that tensor on CPU, and the computations will be done there. If it's GPU, it will transfer that tensor to the GPU and will do the computations there. If you're using mixed devices, then you'll get an error message. You cannot have a tensor on the GPU, a tensor on the CPU, and do a multiplication or something like that. It doesn't work. Okay. So here you can see that I have created this matrix, and it is stored on the GPU of my computer. Yes?
Is there a default for device, or do you have to always?
Pardon me?
Is there like a default?
The default is CPU. Yeah. So you don't necessarily have to run that code. The default is CPU. Yeah. Okay. And there's the syntax 2.2, and then you can transfer tensors between GPU to CPU and vice versa. Okay, so for example, here I have transferred X to CPU, and then now if I check the device attribute, wait. Nope. Okay, yeah, I have to reassign it, I guess. Okay. Yeah. Okay, and we can do the transfer like that. And if you have a CUDA GPU, then it is a similar syntax. All right, so this is not really that much important detail at this point. It's just for you to see, okay, PyTorch can deal with computations on both CPU and GPU, and when it comes to picking one, then it's just a line of code to transfer stuff between GPU and CPU. Yes?
So every time that we define a tensor, we need to set like where do we want
Yes.
set?
Yes. If you don't do that, it will. So if you have set the device in advance, then it will move everything to that device. If not, then you have to specify the device.
So it's not specifically for calculation, but also like for creating variables.
Yes. Yes. Okay. Questions? Okay. So, well, to recap, what's important here again is that we have an interface, looks like NumPy. We deal with multidimensional arrays or tensors. That's all good. That's very similar to Python. And we can do computations on GPU. It makes things extremely faster. So that's the main takeaway here. All right, now let's move on to the next very, very important topic of automatic differentiation. So this is the most important thing here in this lecture, in my opinion. Let's see what this is. So, suppose that we have this array, x equals this value, which is just a single value. All right, and now let me do this math operation. So x squared plus x, and I save the results in y. Okay. Now, if I only give you y, there is no way to trace back the computations and see what kind of computations has been done on x to lead to this value of y. There is no way of doing that in NumPy, right? And generally, when you compute something, there is no way, there is no record keeping, basically. You just have the value, the result stored in the memory, and that's it. Okay, and that's fine. That's fine. But for the purpose that we have here, it's we have to have We have to keep record. Okay. So what PyTorch does is that it enables us to track computations done on tensors. If you ask me what is the most important thing that PyTorch does, I will say this is the most important thing. We are able to track computations. Okay. Let's see how that's done. Okay, so before that, but what's the purpose of tracking computations? That's an important question. And then the answer is, if we know exactly what kind of operations have been performed on X to give Y, we'll be able to compute the derivative of Y with respect to X, and that's thanks to a rule called chain rule. Let's see how that's done. Okay, so suppose that we have the computations that we have done already, and now I can say that Y, that variable, is constructed in this way. So first of all, so we had x squared plus x. Okay, so we can say that if we supply x to a function called f1, it will give back to me just x itself. That's the first operation. Then the second operation is raising x to the second power, right? That's the second operation. The third operation is that I add x squared to x. So there are 3 steps in order to get from the value of x to the value of y. There are 3 mappings, 3 transformations that I need to do in order to get from x to y, right? So I can say, in function terms, it looks like something like this. So we take f1 of x. Okay, f1 of x just gives me x, right? f2 of x raises x to the power of 2. So here we will have x squared and x. And function f3, what it does is just adds those 2 terms together. So at the end, I'll arrive at x squared plus x, right? So I can say that these operations that I have done are essentially equivalent to this. I can express them in this way. Okay? So now, if I want to compute the derivative of y with respect to x, I can just use the chain rule, because I know my functions, I know the transformations, and I have chain rule available to me to go back from the outermost value or function to the innermost value or function. So dy to dx is equal to, I messed up the notation. Okay, so this should be a little bit different. I modified this. Sorry about this. dy to df3, df3, 2, and df2. Okay. All right. Again, dy to df3, yeah. Or did I miss something? Oh, 1. Sorry, that should be 1. Sorry, yeah. Okay, that's right here. Okay. Okay, this is because I changed the numbers here last night, the indices of the functions. Okay, so essentially what I can do is that I can say the derivative of y with respect to x in this instance is equivalent to evaluating this expression. So dy to df3, and then I go inside of that, df3 to df2, and then df2 to dx. That's the first part. And then because I have another term over here, I have to create another expression here, dy to df3 again, and then again df3 this time with respect to df1, and then df1 to dx. So basically, you can see that if I know what my functions are, what my transformations are, I can use the chain rule to compute the derivative of y with respect to x. Questions? Okay, once again, let's take a look at the function over here. We have x squared plus x. And the idea is that if I keep track of the computations and know what kind of transformations I have done on x, then because I know the derivative of each kind of transformation that I'm doing on x, then I can use the chain rule to go back from y all the way to x and compute the derivative of y with respect to x. Okay, and now you can imagine with this method, it doesn't really matter how complex the functions are or how many operations or how many transformations I'll do on my values of x, right? It doesn't matter because whatever it is, if we know the derivative of those small components, then I can always compute the derivatives of the end result with respect to the beginning value. Okay, so here if we do this, we'll get the result of the derivative as we have here. And if you just used your calculus skills, it will be just x squared plus x, it will be 2x plus 1. And we get the same result from doing the chain rule as well. So in this case, it's pretty simple. We don't usually use chain rule in this case, but we can use this method and we will arrive at, and then we can generalize this to more complex cases. Okay. So the main idea is to break down any function of x to the most elementary computation or transformation. And then, because we know the derivatives of those elementary computations or transformations, we can use the chain rule to compute the derivative of any complex transformation, which is just a composite way of combining those functions together with respect to x. That's the idea here. So this is called automatic differentiation. And it's called automatic differentiation because once you know the derivative of all those smaller components, if you track the computations, then you automatically have the value of your derivative. You don't have to do anything else, basically. And this automatic differentiation gives you the exact value of the derivative. It's not an approximation. It's not an approximation. Okay, so this is what PyTorch mainly does. It tracks the computations for us, and it sees, okay, at this point I'm squaring the value of this tensor. At this point I'm taking the square root. At this point I'm adding another tensor. At this point I'm doing something else. It tracks all those computations, and we already know the derivatives of those computations, of those transformations, so we can always use the chain rule to go all the way from the end result back to the initial value. So how is this useful in neural networks? We'll learn in a bit that neural networks are nothing but a series of simple linear operations combined with some nonlinearities. And because these are the building blocks of neural networks and they never change, we always have some linear operations combined with some nonlinearities, again, which are usually don't change. So we know the derivatives of those smaller components. No matter how large your model is, you can always compute the derivative exactly using the chain rule. Okay, so now let's see an example of this computation tracking in action. Okay, so I'll try to do the same thing that I have shown you previously. So I'm defining this tensor x, okay, value 2.5. And by default, computations are not tracked, and gradients can be taken with respect to x, but PyTorch tensors accept a parameter called requires grad, and by default it's false. And if we set it to true, then PyTorch will keep a history of those computations. So this time you can see that I've used that parameter, and now the value is 2.5, and it says requires grad equals true. Okay, now I have x. Let me do this, x squared plus x. All right. Now you see the result is 8.75, similar to what we had previously. But you also see this thing showing up, grad fn add backwards. Okay. So this is appearing because, for example, in this case, the add backward or adding operation is the last thing that PyTorch has done, because the last thing is that it has added these two these two terms together, and it shows you the last function applied on that computation. Okay, so it's kind of telling us that, hey, I am tracking the computations. Okay, now how do we compute the gradient? Yes?
So since x has that parameter, there's grad equal to true, and we did some calculation based on x. So does that parameter actually pass down to y?
No, it will be passed down to x itself.
Okay, so
Yeah.
all time.
Yeah, so the gradient, we'll get to that. Whenever we compute the gradients are always stored with respect to the independent variable. Yeah. Okay. So, we'll learn in the next lecture about a procedure called backpropagation, and it's basically about updating the weights and parameters of our neural network models based on the values of the gradient that we have. And I will show you that in the next lecture, but here we'll do a mini or toy version of backpropagation. So PyTorch provides a method called .backward, and it is available on every tensor that has that gradient computation equal to true. And basically what it does, you apply .backward on the variable that stores the end results, and it goes backwards from that variable all the way to the initial variable, okay, and computes the derivatives or the gradients. So here, because y was the end result, if I do y.backward, nothing shows up, but it has actually stored the value of the gradient, which is this, which is number 6, in the attribute grad of the variable x. So now, if I check out x.grad, I will see 6. And you can see that the derivative was computed automatically, just by using the magic of computation tracking. So no matter what kind of operation you do on x to get y, you can always do .backward on the end result, and the gradients will be computed along the way, all the way back to the initial value of x, and will be stored there in this .grad attribute.
Only if requires grad.
Only if requires grad is true, because that's what enables PyTorch to create a basically computational graph. We'll discuss that in the next lecture. So otherwise, it will be just a plain simple tensor, just like NumPy tensors. Okay. So, yes.
So if you were to compute, say, y and z both from x, then would x.grad just return whatever, like you did y.backward or z.backwards, whatever you did last?
Yes, that's right. That's right. Yeah. So how does this help? The thing is, the most, let's say, the most difficult thing to do with gradient descent that we kind of skipped over was computing the gradient. But in that case, with linear regression, we knew the gradient of the loss function. Okay, so we didn't discuss that at all. In that case, we knew the gradients analytically. However, we will learn a bit about neural networks, large structures. It can have any architecture or structure that you like. In that case, you no longer need to worry about the structure of your model. So basically, what the model is does not matter. You don't have to worry about that when it comes to computing the gradients, right? Because in any other case, if you have a model, a particular structure for your model, whether it's nonlinear, it's linear, whatever it is, you have to be able to compute the gradient to do gradient descent. In this case, you just do nothing. You just create your model, do your computations using PyTorch, and put this requires grad to true, and you will automatically have your gradients computed for you whenever you want. Okay. So again, we don't need to worry about the structure of our model by using automatic differentiation. Okay. So I think it's a good point to take a break. Let's be back in 3 to 4 minutes. All right, we are back. Okay, so we've learned that in gradient descent and in stochastic gradient descent, we need the gradient of the loss function to adjust the weights. Okay? So, in order to see why this automatic differentiation helps is that to think about it in terms of saying, okay, what is a loss function? Is it anything other than applying a series of mathematical operations on the inputs? No. So in the case of linear regression, for example, we had x multiplied by some weights, and then we subtract something, and then we square that, and then we sum a bunch of terms together. So you can see that we are dealing with a bunch of elementary transformations, elementary operations, and we know the derivative of all those single operations. So we can use the chain rule if we are tracking the computations, and then we can compute the derivative of the end result, which is the loss function, with respect to all of the initial values, which are the weights in our case. Okay. So this is the code that we had for our gradient descent function. We had an initial guess for w, and then we analytically had the derivative of the loss function. The g here is that. And then we had this dw, which was the step, learning rate multiplied by the gradient, and then we update the value of the weight. Okay? If we want to express that in terms of automatic differentiation in PyTorch, this is what the code looks like. Okay, so we have our loss function here. It's not the derivative, it's the loss function itself. We do the computations, and then we simply do MSE, which is the loss, dot backward. And as soon as we do that, the gradient of MSE with respect to W will be calculated and will be stored inside of those weights. And this is so distracting. Excuse me, I'm here. You're having a class. Yes, I'm just. Okay. Okay, and okay, you can see here when I do the backward, the gradients are computed, are stored inside of W. X and Y are constants, and we don't have requires grad true for those, but we have requires grad true for W. Okay, this is why we're only computing the gradients with respect to W, and the rest of it looks very similar. The gradient is stored inside of the dot grad attribute, and we just do compute the step alpha multiplied by g, and then update the W. You can see that in terms of the code, it looks very similar. And now we understand what the MSE.backward does. Questions about this? This is kind of what we will see all the time in neural network training, yes?
Okay, so if you had said gradient equals the true on, say, wx and y, then within g.backward, it would update all of those things?
Okay. So the question is, if we have requires grad true for x and y as well, then what happens? Then when we do MSE.backward, the gradient of MSE with respect to w and with respect to x with respect to y will be stored in those variables, in their dot grad attribute. Okay, but we don't need to do that. It will be just extra computations.
All three of those are tensors, then, and they've been initialized.
Yes, all three are tensors, but only requires grad is only true for w. Yes. Okay. Okay, any questions before moving on to the next part? Yes. Pardon me? Oh, okay. We'll get to that. But basically, this means that, okay, in PyTorch, when you have requires grad true for any variable, whatever you do with that variable, PyTorch tracks that operation. So here, because I'm not interested in any operation that should be tracked by PyTorch, I say, okay, in this bit, you compute this bit without storing the gradients or anything. So this bit is not important. The bit that's important is MSE.backward. I don't want to do automatic differentiation beyond this point. Yeah. Okay, yes.
So the value that's returned is like a gradient being evaluated at those values of the parameters, right?
Yes.
Is there any way for you to get a gradient that's not evaluated at certain
Like a symbolic gradient.
like maybe x at x?
No, no. This is only helpful if you want the values of the gradient, not a symbolic expression that, yeah. Okay. Now let's move on to neural network basics. So what are neural networks? Neural networks are another class of parametric algorithms. A linear regression is a parametric algorithm. A nonlinear generalized regression is a parametric algorithm, because in all of those, we decide what the structure of the model looks like, and then we have some free parameters that we have to train in order to optimize them so that the loss value is minimized. Okay, neural networks belong to this class. And just like I told you, a neural network is nothing but a sequence of linear and nonlinear transformations. And you often see something like this when we talk about neural networks. It looks complex, but honestly, it's just, yeah. You have units in here that are nothing but ax plus b. So you have a weight, or wx plus b. You have something like that in those units, and then you apply a nonlinear transformation, and then you sum the results, and that's it. So we will discuss this much more in detail in the next lecture, but here, just based on this structure and the way that we can define it in PyTorch, I will create linear regression in PyTorch using automatic differentiation. Okay, so in neural networks, we call each of these units that you see a sigma on, we call those neurons. And a neural network is, people say that it's inspired by biological neurons. So when a signal, when we have an input signal to a neuron in our brains, there is this action potential thing that if the signal is too weak, then there is no action on the neuron emitting from the neuron. And if the potential is large, then the neuron emits a signal to the other neurons that it's connected to. It's kind of similar here because we receive signal from previous nodes or input data, and it's multiplied by a weight, and then a bias is added to that, just like linear regression, and then it's passed through what's called an activation function, which is the nonlinearity bit. And then if the signal is large enough, then we will have a non-zero value being passed onto the next layer. If not, this value just becomes 0, and we will not get any output from that. So that's the inspiration, but what we see these days as neural networks, I don't think they really resemble what happens in our brains. So this is just a helpful, flexible structure for a model, because we can add as many of these units as we would like. We can add as many layers as we like. So it's super flexible. And because we don't care about the gradients anymore, we have a method, an algorithm to do that efficiently, then we can tweak the structure as we like and basically make it more complex to fit more complex data. Okay, don't worry if at this point this is all a mystery to you. We will go through each and every component of neural networks in this and the next few lectures. Okay, so let's do simple linear regression. Here I create an XY data set, which looks like this. Okay. And then here, just for reference, I fit a model from scikit-learn, a linear regression model, and it looks like that. Okay. And then we can also take a look at the parameters of the model. We have the weight and the bias, or the intercept or the bias. These are the values. And this is the model. And in matrix form, it looks like this. So for each value of, for each data point, for each x value, we have a corresponding prediction. Okay. We can represent this operation that you can see here on a graph like this. So here is the linear model. Okay. We can say that we have a value of x, or a vector or matrix of x, and then that's multiplied by a weight, right? And then we have a constant bias, and then we sum the two, and that will give us our output. So that's the same computation presented in the form of a simple graph, basically. Okay. So now let's do the fitting using PyTorch. Because now we have this structure, we have kind of adapted the linear regression model into something that PyTorch understands, then we can translate it into PyTorch code. Let's see how that's done. Okay.
Does
Yes.
that mean that every individual model that we work with so far is equivalent to a neural network with one neuron?
Yes. The linear models that we have covered in this course that we have worked with, yes, they're equivalent. Any linear model that, yeah, any just simple linear model. Yeah. Yeah. Okay. So when we work with PyTorch, the way that it interface works is that when we want to construct our model, we have to define a class, and we have learned quite a bit about classes in 5.11. I hope you remember stuff from 5.11. And all of those classes that we define should inherit from a top-level class inside of PyTorch called nn.module. And what it does basically is that if you remember inheritance from our Python course, if we inherit from a top-level class, we will basically inherit all of its methods and all of its attributes, and then we can extend those, right? That was the purpose of inheritance. So the same is true about PyTorch. For example, you've probably noticed that with scikit-learn models, we always have this .fit, .predict, .score, all of those methods. This is because all of scikit-learn's models, they inherit from a top-level class. So the same is true with PyTorch. And this is the way that we define the structure of our model. So we define a class, okay? The name of the model is up to us. This is something that I decide. And then we have to inherit from nn.module. And this is the top-level PyTorch class. Okay, in the underscore init method, just like we are used to in 5.11, we call the init method of the superclass, of the top-level class, meaning this class. Okay, this is just to initialize that. And then we add the components that we want. Okay, so here I'm defining an attribute called .linear. And what it does, again, it's a function that's available to us in PyTorch. What it does is that we specify an input size for that and an output size. And it basically just creates a linear function for us. So it says, okay, take this many input features and this many output features and simply do this linear transformation. Like wx1, wx2, wx3, plus a bias, give me the output. That's what it does. Okay, and here in this case, because I'm trying to build a linear regression model, this is why I do this here. Yes?
So using the simple linear regression example, input size is n plus 1 features, and output size is 1?
Just one.
One number? Okay.
Right, right. Okay. So. Because we have a, yeah. Yeah. Okay. So, the next important thing about a PyTorch model class is that we have a forward method. And all PyTorch models have a forward method. It's up to us to define what forward does. So what forward does is that it defines how the data is supposed to flow from the inputs all the way to the outputs. Okay. What it means that if you define your model and then you apply or call your model on X, how should the values of Y should be computed? Okay, so if we take this linear regression model, we apply it on the data set X, what is this model supposed to, so okay, we have defined a linear component, but in more sophisticated models, you might have different components. How are you gonna forward this information, take it from the input and pass it through the model? Because there may be multiple ways to do that. In this case, it's very simple and straightforward because we only have one component. So we say, okay, when I ask you to call the model on X, then simply pass X to self.linear, which we have already defined to be this. Okay? Just pass X through that, and then that's the output of the model. Okay. All right. Now, once we have that, once we have the model class, okay, this is run, it's fine. And now we can instantiate the model just like any class. So I create a model object just like scikit-learn models, okay? It accepts an input argument and an output argument. Okay, yeah, so the input size is 1, sorry. This is, yeah, because the trick of ones is done inside of the node, yeah. Okay, so we create a model, and this is what the model is. It takes X, multiplies it by W, and then adds a bias. This is, yeah, where the, okay. Yeah, adds a bias W0, and then it gives us the outputs. Okay, if I print the model, I say it's telling me the name of the model is this, and this is the only component that it has. All right. There is this function available to us which gives us a nice overview of what the model looks like. For example, in this case, it says that I have a linear layer, and we'll learn about layers later on. This is the output shape, meaning that it can have as many rows as we want. However, the output shape is, it has 1 columns. And then we have 2 parameters, a weight and a bias. And you see the number of total parameters, the memory usage, and everything. So this will be very helpful when we define actual neural networks. Okay, now I can use model.stateDict to see the initial values of the W1 and W0. And whenever you create your model, whenever you instantiate your model, it will be initialized with random values for the parameters. Okay? You can change that. You can initialize to 0, but by default, it initializes with random values. All right, so now the x's and y's that we had were NumPy arrays, so we have to convert them to PyTorch tensors first, and this is what we're doing here. All right, now, this is the important bit. So when I said that calling the model on values of x, this is an example of that. We have the model object, and we can apply that on values of x. So if I do that, yeah, it gives me this. And notice that PyTorch is tracking the computations. Okay, and this value just means nothing because the model hasn't been trained yet. So this is the corresponding y value, which is, this is what the model is predicting. This is the actual y value. We don't expect them to be the same because we haven't trained the model yet. Okay. Now, in order to train the model, there are a few more components. So just bear with me. I know there's a lot to digest in this lecture, but we have to get through that. There's no other way. Okay. So we have to define a loss function. That's what we've been dealing with in the previous lectures. And we have to define an optimization algorithm. So the good thing is that all of those are predefined for us. We don't need to code them ourselves. So in this case, we use the MSE loss from PyTorch, which is the mean squared error loss, what we want. And then we use the stochastic gradient descent optimizer, again, defined in PyTorch. We don't need to code that ourselves. Okay. So here, usually the loss function in PyTorch is called criterion. That's just the name that PyTorch people have given to it. And then here's the definition of the optimizer. So I pass the model parameters to it. I'm telling the optimizer, you have to work on these parameters. These are the things that you want to update. And then supply the learning rate. This is the learning rate that we're familiar with, the alpha. Yes?
Does PyTorch support analytical solutions or only numeric solutions for optimizers?
Okay, yeah, you can define your own loss function. So yeah, in that you can incorporate analytical solution. Yeah.
But does it have it built in? Like if you're doing like a linear regression like this, can you just use, because a linear regression does have an analytical solution by setting
Sure. 0? Yeah, no, you have to define it as a special class, which is a loss function, and then yeah. Okay, let's run this. All right. Now, what we have to do, because stochastic gradient descent works with batches, we now have to create the batches and provide that to the model during training. However, again, in lab 2, you have created your own function that creates batches for you. In PyTorch, this is again already done for us. So when we use this data loader function over here, it automatically creates batches of batch size with this parameter. And then it creates a generator. And once you go through that, it will take batches of data and passes that data to you. So everything is made automatic. We just specify the batch size, and this creates the generator for us. Note that the data loader actually doesn't load anything. It's just the recipe for loading the data. So it doesn't fill the memory with unnecessary data at this point. Once we go through the training, we call the generator, and it's going to pick or pull the data from the data set. Okay, now if I check out the size of the data loader, we have 10 batches because I've specified the batch size to be 50, and we have 500 data points. Okay. And now we can look at one batch here by applying next because it's an generator. So let's take a look at that. You can see that the first batch, it contains 50 rows and contains one column. And then the shape of the response, the Y, is just a vector with 50 elements. So it has taken a batch of 50. All right. So in order to train the model, just like the little snippets that I've already shown you, we have to do a couple of things. So this, first of all, we create an epoch loop and then an iteration loop. You are familiar with these two loops if you have worked on lab 2. You have an epoch loop, an outer loop, and then you iterate over the batches to complete one epoch. And you go to the next epoch, and then you iterate over all the batches and go to the next. So you're familiar with these two loops. So this time, instead of having your own mechanism for retrieving data, you just loop over the data loader to access the batches. Just loop over the data loader. Okay. Ignore this bit for now. Okay. Check out this value. So here I'm applying model. I'm calling model on X. Okay. So it takes the model that I have created, that class, and passes the values of X through the model. Okay. And saves the result in Y underscore hat. Okay. So at this point, you know that because requires grad is true inside of that linear component, it is following the computations. Okay. Now, I have my loss function. If you remember, I've already created this criterion, and it just computes the square distance between these two values. So as soon as I apply criterion, again, there is some other computations done. It tracks those computations too. And then finally, when I do loss.backward, it starts from the loss function and computes the derivatives all the way back to the initial values of W. Okay. Once we do that, the gradients of the loss with respect to W's are stored inside of W.grad, so we have the gradients. And this optimizer object knows how to work with those because we already supplied model parameters to the optimizer. Let's take a look at that now. Makes more sense now. So you can see that we have already told the stochastic gradient descent function that, hey, these are the model parameters. So here, when we compute the loss.backward, then optimizer automatically has access to those parameters, and it's going to update them using this step method. So we say, okay, now that you have the gradients, make an update to the parameters. That's what optimizer.step does. Okay, so the important thing here are these 4 lines. So we compute a y hat, the predictions, and then we give it to the loss function. Okay, this is just regular stuff. Now, because PyTorch tracks the computations, we can do dot backward on the loss value. It automatically computes all the gradients for us with respect to the parameters. Now that we have the gradients, use the optimizer to make one update for you. And it does that by doing stochastic gradient descent, because that's what we've defined, and then updates the parameters. Okay. And then once you have done that, again, you go to the top, you do the same thing on another batch, and then on another batch, and then on another batch, and then you complete one epoch. And then you go to the next epoch, do the same thing for all of the batches, so on, so forth, and so forth. Okay, what is this first line? By default, PyTorch does not erase the gradient values inside of the weight parameters. It doesn't erase that, so we have to do that ourselves. And there is a reason for that. I'll discuss that in the next lecture. That's what it does. Okay, questions about this code? By the way, you don't have to define a function for this code. You can just create your for loops wherever you like. And that's the beauty of PyTorch. It doesn't hide the necessary details of the inner workings of your model. So in TensorFlow, there's another framework called TensorFlow. It basically hides all of those details from you, and I think it's terrible for a person that is just getting started with neural networks. But this is different. Yes?
Just that last step, the losses, accumulating the loss per batch,
Mm-hmm.
and resetting it shortly.
Mm-hmm.
Can you just talk through why that is?
Oh, okay. Okay, so this is because, so we are working inside of an epoch, and for each iteration, I take the value of the loss, and then at the end, I want to compute an average of the loss so that I don't end up with 50 loss values for each epoch. This is just a choice that I make. You can just get rid of that line. I just want to keep track of what's happening, basically. Yeah, I do I compute the average. Yeah.
In data loader, I'm not sure, does it create like random batches here of like size 50? So would each batch like be randomized each time, or?
Yes. So
There's a shuffle.
yes, there is this shuffle argument that basically does the randomization for you. Yeah. Okay. Other questions about this code? Oh, how do we decide on the so we usually have this question from lecture 2 in this course all the way until lecture 8. There is no definite answer for that. So this is an empirical thing. We have to do experimentation. You have to start with some values and then we optimize the values. There are some methods to systematically study the value of the learning rate. I'll discuss those in another lecture. But basically, again, there is no science about that. We have to just try and see. Yeah.
Is it standard to work in terms of epochs instead of iterations?
Yes. Because basically we're interested to see how many times our model has seen the entire data set. Yeah. Yes.
For each iteration based on the epoch, so the data loader has the same patches of the training data, right?
Yeah.
Okay.
Yeah,
So
that's
we
right.
don't need to randomize like for each iteration.
You don't need to do that for each epoch, no. Yeah. I mean, you can if you want.
So it's different from the lab. Like
Yes.
wherever you shuffle for
That's right.
each epoch.
Yeah. Again, that's right. But again, you can do that if you want. Usually the people don't want to. One shuffling is usually enough. Okay. So now, after training, I want to take a look at the model parameters. So they have been updated. Sorry. This is before training. I have just defined the trainer. Okay, that's good. So this is before training. These are the initial values. And now let me run the trainer function. Okay, run the trainer function here. Okay, so it starts from a very big loss and then goes down to 94, from 1500 to 94. Okay, now if I take a look at my my parameters, they are updated. Take a look here. So 0.79 minus 24, here 44.72 minus 0.85. So let's have a comparison with scikit-learn's values. So the true values are this, and we got pretty close. We can indeed do better if we do more epochs. So for example, if I do, for example, 100 epochs, and remember that if I run the trainer again, it will start from where we left off, basically. It doesn't recreate the model. Unless you recreate your model object, it will always start from the previous point. So the benefit of this is that you can do a number of epochs and then stop and then maybe change the learning rate and then do a number of epochs again and do something else. And even you can change your optimizer, anything you want. So it gives you full control of the convergence. So here, another 100 epochs. Okay, let's do another 100. Okay, seems like we're fluctuating around 93. So let's do the comparison again. This is much better. Okay, pretty close. And you can actually converge on the correct values here up to two significant figures if you do more epochs. Yes?
Is there a tracker over how many epochs you've run in general, or do you just kind of, like, you've done 210 now, but it's several hundred?
That's right. Yeah, you have to keep track of that yourself. Again, in PyTorch, these things are left to the programmer. Yeah. Okay. All right. So now, just similar to what we did with a simple linear regression case, we can have multiple inputs and basically do multiple regression. There's nothing stopping us from multiple x's or multiple features, basically. Okay, so here in this case, I have 3 input features and 1 output. Let's generate some data. Okay, and here I do all that stuff of converting things to a tensor and then create the data loader, create the batches. So this is all hidden in this cell. And then now let me create this model and note that here I'm using an input size of 3, and that's the number of features that I have in my data set. Okay. All right, let's do a summary. You can see this time we have 4 parameters. We have a bias and 4 weights. Okay, define the loss, the optimizer, and run the training. Okay, 10 epochs, this is the value that we get. Let's do more epochs, more epochs. Okay. And now let's compare with values from scikit-learn. So these values are pretty close. This one is not that much. We can play with the number of epochs, the learning rate. You can experiment with that on your own time. But it's pretty close. Okay, so it seems that we had a lot to cover, and I'm not going to be able to cover the next section today, but I think we got through the most important stuff here. So we've discussed what PyTorch is, that it works, is able to do computations on GPU, and it also enables us to do automatic differentiation. And once we do that, we define our model using a PyTorch class, and then we have defined our trainer to compute the loss, and then do a backward to compute gradients, and then update the weights. And we essentially imitated what we have done in the previous lectures in the PyTorch framework. Questions before ending the lecture? Yes.
Is the output size defined by how many classes or elements like we're expecting? Because with the logistic regression case, we have just one node at the end, and then the linear regression also have one node because we have one prediction. But then when we have like a multi-class prediction, we would end up with
Exactly. Exactly, yes. Yes, that's dependent on the kind of modeling that we do. For a multi-class modeling, I have that at the bottom of this notebook. You have multiple classes and probabilities for those classes, yes.
Is there a point also to like setting the output size to be larger? Like, would it be more generalizable if you end up converging?
You mean the output size being larger, you mean the number of dimensions, or?
Yeah, I guess like if we're
But-
thinking about multiple layers, is there a case where you don't want it to converge all the way?
Okay, so the last layer should have as many dimensions as your actual output values in your data set. So that's set. But in between, yes, we can add more layers, and we will discuss that later. So today, we didn't discuss hidden layers or anything like that. We have only created or imitated the linear regression model here. Yes.
The nonlinear regression with the neural network is not required for lab 2.
Yeah, just lab 2 has a lab 2 problem.
It is not required in that sense, but okay, that's right. I mean, we don't directly maybe use that inside of the code. You don't have to do anything with that, but you have to understand the meaning of it. I didn't want to rush through that because it's a pretty important topic, but let me give you, because we have maybe 5 minutes left, let me give you an overview of what this is. So basically, okay, suppose that the function that we're trying to approximate is not linear anymore and it has a shape like this, and obviously if we fit a line, it won't really do a good job of fitting to the data. So in neural networks, what really enables us to do powerful modeling is the fact that in neural networks we have nonlinearities. Okay, and those nonlinearities are provided to us by applying what's called activation function in between the layers of our neural network. So in the examples that we have just seen, we simply multiply the inputs by a weight and then add a bias, and that's the output. However, in a nonlinear neural network, we do that, multiply by the weights, apply a bias, and then we pass the result through what's called an activation function. Let me show you what that is. One very common activation function is the sigmoid function. Okay, let's take a look at the sigmoid function. Okay, it means that when we receive the output from that node, that neuron, we pass it through this, and you can see that if the value is too small, then they say that this neuron is not activated. So we'll get zeros for any value smaller than -5, right? And then for values that are much larger than 0, we will always get 1. So the neuron is fully activated and it takes all the data and passes it to the next layer, whatever the next layer is. So this is the idea of the nonlinearity that's there. For some values, it's not activated, it just sends 0. For other values, if the signal is strong enough, it will send that signal to the next layer. Okay. So essentially, we can do something like this. We have X. We have 3 neurons. Okay, each neuron simply just multiplies the input by a weight and adds a bias. What adds the nonlinearity here is that we then pass this thing through this sigmoid function to add the nonlinearity, and then this is one layer. Okay, and then for the last layer, again, we multiply the signal that we have received from the previous layer by a weight, and then add a bias, and then sum the results. Okay, this seems like it's something arbitrary, like it's just magic. We do this and it works. I wanted to show you to build an intuition for you why this works and why this works so well, and I'll do that in the next lecture. But basically, this is the gist of it. We have the linear neurons, and then we pass those through nonlinear functions to enable that nonlinear adaptation.
Is the unit of x on the sigmoid function there? Is that like how close the initial function got to like what the loss of the initial linear function is, and that if it's a lower loss